Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through chapter 6.3 and looking at linear systems with non-real eigenvalues. In chapter 6.3, we will continue our study of linear systems of differential equations with constant coefficients by learning the case for which the eigenvalues and eigenvectors are complex. Given a linear system of differential equations, x prime equals ax, we will still look for the eigenvalues using the characteristic equation determinant of a minus lambda I equals 0. However, if the quadratic equation has a negative discriminant, that's the part underneath the square root, the solutions for lambda will be complex conjugates. And you would have seen this already when we looked at chapter 5.3. The general form at that time, we wrote it as a plus I beta and a minus I beta for our two complex eigenvalues. The corresponding eigenvectors will also be complex conjugate pairs and can be written in the form p plus iq and p minus iq. Now, the general solution, it can still be written as a linear combination of each of the eigenvalues and eigenvectors. However, to analyze the qualitative behavior of these trajectories, we need to be able to write these solutions in terms of real quantities. Because as it stands now, both lambda, our exponent, and our vectors have complex components to them. So let's see about rewriting these. And to rewrite them, let's consider just one of these terms for a moment. The e to the lambda 1 t v1. Now, if we substitute in here what our eigenvalues and eigenvectors look like, then we'll get the expression e raised to the alpha plus I beta times t times our eigenvector, which is going to be of the form p plus iq. And we seek to rewrite this without the complex imaginary, or the complex parts, without the imaginary part I. And so let's look at rewriting this. Maybe the first thing we can look at is how to rewrite this exponential term. Maybe distributing that power of t, we can write this as e to the alpha t plus I beta t And now, using properties of exponents, let's rewrite this exponential term as the product of two exponentials. So maybe we'll write it as e to the alpha t times e to the I beta t. Now, by Euler's formula, we can rewrite this exponential term, this e to the I beta t, as e to the alpha t times cosine beta t plus I sine beta t And now what I would like to do is distribute or FOIL these two parentheses terms. So we'll do our normal distribution. The e to the, or the cosine times the p term, the cosine times the iq term. And so we'll get e to the alpha t times cosine beta t times your p vector plus I cosine beta t times your q vector Now let's distribute the sine term to the p vector and to the q vector. To get plus I sine beta t, and then I times I, what we know as I squared, will be minus 1 sine beta t times our q vector. Now what I would like to do is regroup your real terms and your imaginary terms. Your real terms is this cosine beta tp and this minus sine beta tq. So let's regroup these two and write it as e to the alpha t times, well, I think I want to, no, this is fine, times cosine beta t p vector minus sine beta t q vector. Now the remaining two terms both have an imaginary component, an I term. So let's rewrite those two grouped together. And I want to write them in the order where the p vectors always come first. So I'm going to write the sine beta t first times your p vector plus the cosine beta t times your q vector. So what I wanted to illustrate there was, notice how we wrote this in the form where it was p, then q, p, then q. And this is just our author's choice for how they decided to organize this. Now, written this way, we want to identify that this is referred to as the real portion of your solution. And our author writes this as x real. And not including the I, this is referred to as the imaginary portion. And as we showed previously in an earlier chapter, the real portion of a solution and the imaginary of a portion of a solution are each individual solutions to our differential equation. And since this real portion of the solution and that imaginary portion of the solution, we can write our general solution as a linear combination of these. So x of t, our vector solution, is going to be some c1 times your x real part of t plus some c2 x of your imaginary part. And this is the general form of your solution. Where the real portion and imaginary portion are each defined as we've written there. Of course, I'd like to show you how to manipulate this with a specific example so you can see how we write our solutions. So let's get right to that. Consider the linear system of equations presented by this matrix. We would like to find the eigenvalues and eigenvectors of this system and then write the general solution to the linear system. So let's first look for our eigenvalues. And of course, my preferred method for finding the eigenvalues is using this characteristic equation of the form lambda squared minus the trace of A times lambda plus the det of A. Of course, when you look at this, recall that the trace of your matrix is the sum of this main diagonal. So here the trace of A is 10, and the determinant of A would be 6 times 4 is, remember, it's the product of your main diagonal, so 24 minus this negative 5 gives us 29. So our characteristic equation is going to look like lambda squared minus 10 lambda plus 29 equals 0. Now in our previous sections, chapter 6.2, this characteristic polynomial was always factorable. However, in this scenario, nothing multiplies to 29 and adds to negative 10. So we're forced to use the quadratic formula. So here our eigenvalue would be lambda is equal to the opposite of your b term, so 10, plus or minus the square root of b squared, so 100, minus 4 times the product of a and c, so 29. I'm just going to write that a little bit neater. All divided by 2 times a, or just 2. And notice the discriminant here, the 100 minus 4 times 29. This ends up being, well, it's 100 minus 116, or negative 16. And the square root of negative 16 gives us our complex number. So 10 plus or minus 4i all over 2 or maybe we'll write it as just 5 plus or minus 2i. So here the real part of our eigenvalue is 5, and the complex part, the beta, is going to be 2. Our author always uses the positive version. Okay, now let's look for our eigenvectors. To find our eigenvectors, we're going to use the equation a minus lambda I times some vector x equals the 0 vector. Now remember, we always subtract lambda off of the main diagonal when we're looking at a minus lambda I. It just happens to be that here our eigenvalue ends up being complex. So grab our original matrix, and we're going to subtract lambda off of the main diagonal only. So here we're going to have, for the eigenvalue, lambda 5 plus 2i, it'd be 6 minus 5 plus 2i. And I strongly encourage you to make sure you use parentheses here to make sure that you have to distribute that minus sign to both terms. Minus 1, 5, and then 4 minus the 5 plus 2i. Times some vector x will give us the 0 vector. Now, because we did use those parentheses, let's remember to distribute the minus sign and combine like terms to simplify our matrix. So it would be 1 minus 2i, negative 1, 5, negative 1 minus 2i. Times some vector x, which will have two components, equals the 0 vector. Now recall what lambda does for us. When we look at A minus lambda I, this matrix is always going to be singular, which means one of these columns or one of these rows has to be a multiple of another. This helps us when we're looking for our eigenvalues, because I'm going to look at just the first row of our matrix product. So looking at the first row times that column xy, we'll have 1 minus 2i times the x component of our vector minus 1 times y has to equal 0. And so here we get to choose to let x be some value. I'm going to let x equal 1. Because if x is 1, then we get the equation 1 minus 2i minus y equals 0, or that y has to equal to 1 minus 2i. This allows us to write our eigenvector x as a vector whose x component is 1 and whose y component is 1 minus 2i. Now in chapter 5.3, this is where we said we could stop. However, in chapter 6.3, we want to write this vector x in terms of a real and an imaginary component. And if I scroll back in our notes, we like to write it in this form: p plus iq. So a real portion p plus an imaginary portion q. And that's as simple as rewriting it as the sum of two vectors. The real component will be 1 and 1. And then the imaginary component is going to be 0 and negative 2i. Notice if you add these two vectors together, you're back at the same as the original. However, we want to write it with the I factored out, so I want to see it as 1, 1 plus I times the vector 0, negative 2. And written in this form, this is the P vector that we're talking about in our formula, and this is the Q vector, the part that does not have the I. Now that we have our eigenvalue and our eigenvector written in terms of the p and q vectors, we can jump to our general solution. So for our general solution, remember, we want to write our general solution as the linear combination of the real portion and the imaginary portions, where the real portion is written as this expression and the imaginary portion is written as this expression. Okay, so here we go. So our real portion now is going to be our e to the alpha t, so e to the 5t times the cosine of beta t, 2t, times our p vector, 1, 1. Now it's going to be a minus sine beta t times our q vector, which, if we decided to simplify this by multiplying the cosine expression into the vector, the sine expression into our vector, and then combining these two terms, I think we should be able to get e to the 5t. Now our first component would be cosine times 1 minus sine times 0, which is just going to be cosine of 2t. And our second component is going to be cosine of 2t minus sine beta t. I don't know why I wrote beta t there. I should have wrote 2 times negative 2. So cosine 2t, and I think it'd be plus because they're double negatives, 2 sine 2t. And that's the simplest version of our real component of our vector. Now the imaginary portion is going to be e to the alpha t, so e to the 5t. Now remember, the order changed. Now it's going to be sine of 2t times our p vector plus the cosine of 2t times our q vector. And again, I'd like to simplify this by writing it as a single vector quantity. So let's distribute the sine to the first vector, distribute the cosine to the second vector, and then add these two quantities together. So I think we're going to get e to the 5t times the sine of 2t, and our second component is going to be sine of 2t minus 2 cosine of 2t. That's our imaginary component. Which allows us to now write our general solution as a linear combination of these. So it'll be x is equal to c1 e to the 5t Now our real component was cosine 2t Second component was cosine 2t plus 2 sine 2t plus c2 times our imaginary component, which had a sine of 2t sine of 2t minus 2 cosine. Now this is a great form for our general solution. However, here it is common to rewrite this one more time, because you'll notice that there's a common factor of e to the 5t on both of these terms. So another common way to rewrite this is to factor out that e to the 5t and write this as e to the 5t times c1 times your first vector plus the c2 times your second vector quantity. Notice that both of these forms are equivalent and acceptable. However, in past semesters, it seemed like a majority of my students would write the answer in terms of this second form. Maybe because there's less factors of e to the 5t to write. And obviously maybe there's some places you could skip some steps. Once you identify what the real and the imaginary portions of your solutions are, you can probably just jump right to the second form of your solution. Now, the second question that we want to consider with this example is, what does our phase portrait look like? How do we graph solutions to this in the phase plane? Now, to help us with that, we need to look at a little bit more theory. So let's jump to the sketching phase portraits notes. When the eigenvalues and eigenvectors of a system of linear differential equations are non-real, we will see spiral and elliptical phase portraits. This topic was originally introduced in chapter 2.6. You can reference that chapter if you'd like. However, I'm going to summarize the process here. For a two-dimensional DE system, x prime equals some function of x and y prime is some function of x and y, we define the V nullcline, or also written as the vertical nullcline. Is the set of points with vertical slopes. This only occurs by solving for when your horizontal component is 0. Now, if you have a vertical slope, it means your lines are going straight up and down. But that only happens if x prime is 0, meaning you have no horizontal movement. Your H nullcline, also referred to as your horizontal nullcline, is the set of points with, and I notice a typo here, horizontal slopes, meaning they only go sideways. This only occurs on when y prime is equal to 0, meaning you have no vertical movement. So the method that we're going to use to find our phase portraits is to find your vertical and horizontal null lines and sketch those. Determine the direction of movement on the null lines. For example, on your vertical null line, are you moving up or down? On your horizontal null line, are you moving left or are you moving right? So determine the direction of motion on the null lines. Determine the direction of motion in each region created by the divisions of the null line. So here we're saying if you had picked a point that was here, notice that this point would have to be moving up if it agrees with this null line, and to the right if it agrees with this null line. And in general, points in this region are going to be moving up and to the right. Similarly, in this region, if you're agreeing with these null lines, you have to be moving left. This null line would tell you you're moving up. And in general, solutions in this region will always be moving up and to the left. Let's continue this for the last two regions. In this region, if you're agreeing with this null line, you have to be moving to the left. This vertical null line says you're moving down. And in general, solutions in this region will be moving down and to the left. Lastly, if you picked an initial condition that was someplace in this region, you'd have to be moving down and to the right. And in general, you'll be moving down and to the right. So determine the direction of motion in each region created by the divisions of the null lines. And then lastly, sketch a trajectory that follows the directions of the direction field elements that we just created. So let's look at our example. Let's sketch the phase portrait for this system. And notice this is the same system as our last example. Let me scroll back so you can see that. Here we started with the system x prime is this matrix times x. And notice the components are the same components. 6, -1, 5, 4. But now we want to sketch the phase portrait for this system. So to start with, let's rewrite this matrix equation back as a system of equations. So if we let our vector x be a vector with two components, x and y, then here we're going to have the derivative of xy, and this will be the same as your matrix times our vector xy. Our first element over the left hand side will be x prime. The second element will be y prime. Now if we do our matrix multiplication on the right, remember the way we did this is taking the first row of our matrix A times the first column. This will give us 6x minus y, and our second element, our second equation will be 5x plus 4y. So this is our matrix, our system of equations that came from our matrix equation. Now the first thing we want to look for is our vertical null line, our V null line. Now our vertical nullline has vertical slopes only. And this only happens when x prime is 0. So if you're thinking y prime is your vertical movement, x prime is your horizontal movement, then your vertical nullline will have vertical slopes only when x prime is 0. So grab your x prime equation, which is 6x minus y. And we want to find out when this is equal to 0. And we're always solving for y, and so we get the line y equals 6x. That's your vertical nullline. Now we'll find our h nullline. Your h nullline has horizontal. Slopes only. And if you only have horizontal slopes, that means that y prime is equal to 0. So let's grab your y prime equation. 5x plus 4y equals 0, and solve for y. So we'll move the 5x to the right hand side, I'll make it negative, divide by 4, and I think we'll get negative 5/4 x. Okay. Now let's look at creating our phase portrait. So let's start by creating our coordinate system. With our x and y axes. Oh, I labeled that one x, that should be y. And now draw each of our nullines. Now our vertical nullline, this is the line y equals 6x. So it would be a line with slope 6. And without being terribly accurate, it'd be a line that'd go 1 to the right and 6 up, and maybe it'd go through this point right here. So let's draw the best line we can to represent a slope of 6. And I have a hard time doing this on my tablet, but it would look something like that. Now let's also draw our horizontal nullline. Our horizontal nullline is defined by the line negative 5/4 x. So it would have a negative slope, a little bit steeper than -1. And without being terribly accurate with my points, it looks like it would probably be a line that looks something like this. Now remember these nullines. The first one was a vertical nullline, meaning that we only had vertical movements. So things on this one only went up or down. And our horizontal nullline, the negative 5/4 x, only had horizontal movements. Now we still need to determine the direction of these movements, left, right, up, or down, but I do know that this one was our v nullline. So only vertical movements. And this one was your h nullline. So only horizontal movements. Now let's determine the actual direction of movement on these lines. And the way we do this is we pick a test point. Imagine a point on this line might be the point where x is 1, and if x is 1, y is 6. Now if you plug the ordered pair 1, 6 into your x prime equation, 1 for x and 6 for y, this ends up being 0. And we knew that because it was a vertical nullcline. We expected there to only be vertical slopes. And that's because your horizontal x prime is 0. But when you plug 1, 6 into your y prime equation, notice what you get is 5 plus 24 is 29. Now I don't really care that its value is 29 as much as that it's positive. It tells me that this vertical nullcline at the point 1, 6, it has slopes that move upwards. Let's do the same thing for another point on our vertical nullcline on the other side over here. And to find a point, just pick an x value. If x is -1, then when you plug into your equation, y is going to be -6. And let's go back to our system of DEs. Here, x is -1 and y is -6. I think this will be -6 plus 6, and it's still 0. And I'm expecting x prime to be 0 because it's a vertical nullcline. But when you plug in -1, -6 into your second equation, this ends up being negative, which tells me at the point -1, -6, our y prime component is negative. Meaning solutions will have to be moving downward here. Now you might notice that these directions are opposite from 1, 6 and -1, 6. That will always be true. When one nullcline crosses the other, the directions of movements always switch. That tells you technically all you had to pick is the ordered pair 1, 6, and then the other point, -1, -6, had to be going in the other direction. Let's try this again though on the horizontal nullcline. And let's pick a point that lives on this line. And the easiest way to do this is to pick an x value. And when I look at our equation, I think one of the easiest x values to pick is x equals 4. If x is equal to 4, y is -5. Now, let's go back to our system. Erase our other scratch that we did here. Now we're saying if x is 4, y is -5. Notice this is going to be 20 minus 20. This is 0. And it should have been 0 because this was our horizontal nullcline where we only have horizontal slopes, which means y prime had to be 0. But if you plug 4, -5 into your x prime equation, this will be 24 plus 5 is 29. And I don't really care as much that it's 29 is as that it's positive. And that tells you x prime, your x movement is positive. So that at this point, for -5, solutions have to be moving to the right. Our last point to consider is this point. And again, the easiest way to pick this point is to pick an x value, like maybe choose x is -4. But if x is -4, the y value is going to be +5. And what I would like to confirm, that direction of movement on this nullcline has to be to the left. If here it's to the right, at this point it has to be to the left. But let's confirm that. Let's plug in -4, +5 into our y prime equation. No, this will be -20 and +20. This is going to be 0. but when you plug in -4 and +5 into your x prime equation, this will be -24 minus 5 is -29, so x direction has to be moving in the negative direction. So solutions here have to be moving to the left. In general, you don't have to pick or do the algebra for your second point. Just notice they're always opposite in direction. Okay, now let's consider what our phase plane is going to look like. And if we look back at our original solution to this system of equations, I'm noticing that both of these components have a exponential portion with a positive exponent. This tells me that as time goes on, solutions will get larger. They increase. And the trigonometric quantities, this tells me that there's going to be a cyclic pattern. So you have a cyclic pattern that increases in value over time. So in our phase portrait, we should expect to see spirals that increase in size, move further from the origin, and follow the directions of these null lines. So if I was to start maybe at the origin, let's do this in another color, you would expect solutions to, well, let's actually fill in what's going on in each of these regions. I skipped that. So let's consider this region here. At this point, solutions will be moving up and to the left. It matches the movement touching the two null lines. And so in general, it has moving up and to the left. If you were in this region, you have to be moving to the left and down, and in general, down and to the left. In this region, you have to be moving down, because it matches your vertical null line, and to the right, and in general, down and to the right. And in this region, you have to be moving to the right and up, and in general, up and to the right. Okay, now let's draw our curve. If you started at the origin and you moved up into this first region up here, you'd have to be moving up and to the left. But eventually you'd have to cross that horizontal null line only horizontally. Then in this region, you're moving down and to the left. Eventually you'd cross this vertical null line and only moving vertically. And if you imagine continuing this, it would make this spiral pattern. Now it's a little challenging to make this look really accurate, but let's try one more. If you were to start by moving in this downward direction, you can imagine a spiral that might look something like that. And this is the general behavior of your system of equations trajectories. They move in an outward spiral position. Now, it might be nice to confirm this using your phase plane plotter. So if you have a moment, go pause your video and look at the phase portrait plotter and see if this agrees. However, at this video, we're at 49 minutes. So I'm going to stop here and look at a couple more examples in another video. And I'll look at some of those phase portraits with you at that time. I hope this is helpful, and I'll see you in our next video.